So, what's string theory? Well, string theory is a theory for everything. It consists of these tiny, very microscopic strings that we can't even see with our naked eye, or probably won't even ever see, that vibrate a bunch of energy. And this theory is supposed to bring unification to two very different forces that are supposed to make up the laws for our entire universe, but the two laws don't make sense together at all. You see, Albert Einstein was intrigued with Sir Isaac Newton's findings, so he took it upon himself to elaborate more on this. He figured out exactly what gravity was, and that Sir Isaac Newton's prediction on that gravity is has the fastest velocity than any other forces, well, it was wrong. Albert Einstein, he concluded that light was the fastest velocity. You can compare these gentlemen's findings with a very certain scenario. Take, for example, that the sun just suddenly vaporizes and vanishes. On one part of the comparison, you have Sir Isaac Newton. His theory was that as soon as the sun vaporized, that the planets would fly out of orbit into space instantaneously upon the sun's action. On the other side, you have Albert Einstein, and his theory brought up the question, how could Earth disappear before seeing the last light of the sun? Well, this brought into a bunch of experimentation, which proved that the approximation of the light that travels from the sun to us is about 8 minutes. And by the time the last of the sun's rays would hit us, would be about the same time as when Earth's gravitational pull would be released from the sun. And this disproved Sir Isaac Newton's argument. This also proves that gravity doesn't exceed light's velocity, that they're probably about the same speed. Einstein's argument with Newton was also the basis for a new theory that he came up with called general relativity. Now, general relativity can be explained almost as if you were to place a bowling ball in the middle of a trampoline. The trampoline would curve into where the bowling ball was, where it sat. It warped space-time. If you were to take Earth as a little ping pong ball, suppose, it would circle around where the most gravity was. And also, apart from this theory, you have to include that nothing can travel faster than the speed of light. So that's basically the basics for general relativity. It shows that space-time can warp, giving us three dimensions of up and down, left and right, back and forth, and a dimension of time. Einstein also concluded that if you take electromagnetism plus the fact of general relativity, you would equal the amount of unification, or a theory to the entire universe. But what really is electromagnetism? Well, electromagnetism is the combination of electricity and magnets, and these two components share some strange bonds. A scientist by the name of James Maxwell found that you could really see these strange bonds if you sit on the top of a mountain in the middle of a thunderstorm. You see, a compass will always point north, but given a random spark of electricity, say lightning, on the very top of a mountain, your compass just spins wildly out of control. And this shows some of the strange bonds between electricity and magnetism. In theory, string theory would be able to unify these two forces. But there's kind of a catch. Electromagnetism can kind of overpower gravity. Take for an example if you were to jump off a building. Yes, you're going to plummet to Earth because gravity is pulling you down towards the center of the Earth. But when you hit the pavement, unharmed hopefully, you don't go straight down to the center of the Earth's core. That's because of electromagnetism. Because everything of matter is made up of atoms. And these atoms, they have a negative charge. Everything in matter has a negative charge. And two things that are similar will repel each other. They won't. Thus, electromagnetism stops us from traveling down straight to the center of the Earth. Well, electromagnetism isn't used for something as big as the planets, as general relativity, but it's used for something smaller. Small as in atoms, maybe? This brings us into quantum mechanics. Now, quantum mechanics, it's kind of weird, to be honest. You're shrunken down to something billions and billions of times smaller than what we are right now. You get shrunken down, and it's very radical. Everything's crazy and wild, and nothing's determined. Everything is by chance. It's like throwing darts at a dartboard. You're never guaranteed one specific spot on the dartboard. It's going to be scattered and random. In quantum mechanics, there's no definite set of rules. You're just guessing. You don't have one certain answer. The answer isn't one. It's all of the possibilities that you can get as the outcome. Quantum mechanics on a subatomic level can describe how our universe works. In quantum mechanics, you have electromagnetism, plus you have two other forces, called the strong nuclear force and the weak nuclear force. The strong nuclear force is the binding of between protons and neutrons, and the weak nuclear force is turning neutrons into protons. This can also produce radiation, and it's effective in our everyday life. Gravity and the sense of quantum mechanics, well, they really don't get along together. It's like if you were to take the Capulets and the Montagues and put them in a house together. There'd be sheer terror and a lot of very dramatic chaos. That's what it's kind of like for gravity and quantum mechanics. They can't coexist peacefully. So everything's split into two classes. One class of general relativity that measures big things, like stars and planets, galaxies and universes. And then you have quantum mechanics, that measures little tiny things like atoms and quarks. But is there a place where these two could be possibly used? Well, there is, and it's called a black hole. A black hole can be made as when you take something huge, like if you were to take Earth and shrink it down to the size of a peanut. It would disrupt the space-time and warp it, so it would turn into this giant hole where nothing could escape, not even light. So which would be used? General relativity or quantum mechanics? Well, they can't coexist peacefully. So there's got to be something that can combine them both together without there being chaotic or monstrous disasters. In string theory, everything is made up of strings. Little tiny, almost like rubber band-like things that are smaller than quarks, and we can't see them. So, if you were to put string theory to combine quantum mechanics and general relativity, how could you test it if you can't even see what's really there? Is it even there? So, strings are so small that we can't even test them. So, do we know if it's really there? Well, on a small scale in quantum mechanics, everything's really crazy and bumpy and everything. And all of our real rules in life just kind of, well, they really just break down. And you can describe as the heart of a matter, of anything that's matter, would be a string. And a force would be described as a particle. We can see this in all three parts of quantum mechanics. And the particles in electromagnetism and the weak nuclear force can get so hot, and the two would just melt together, creating the electro-weak force. And we can see this in all three parts of quantum mechanics. And in the hot conditions of all of this, electromagnetism and the weak nuclear force would get so hot that the two would just melt together, creating the electro-weak force. And this also becomes part of a standard model, but it doesn't include gravity. So string theory becomes kind of a backwash and gets pushed out of the way. Deeper and deeper, string theorists went to try and figure out how this could even work. They got some kind of weird results, particles that were unphysical, and a tachyon that was a particle faster than light, which, proposed by Einstein, was completely impossible. And string theory required 10 dimensions instead of the 3 that we know plus time. And it just became all a bunch of craziness. In the equation of string theory, a man by the name of Schwartz found that there was a massless particle that needed to be predicted, but it had never been seen. And in the equation of string theory, you got all of these anomalies. Now, an anomaly is a mathematic error, and in this equation, there was a lot of them. You had to keep brainstorming and kind of replace the entire equation, mixing up the different factors, trying to see if you can get a different outcome to try and at least help him figure out what string theory is and if it was even plausible to use. Now in his research, Schwartz kept digging and discovering, and he realized that maybe the equation that he was looking at wasn't describing string theory, but describing one missing key element needed in the equation, called a gravitron. And indeed, that was the massless particle that was needed to complete part of this equation. Once the equation was complete, he figured out that it was really describing a string, almost like a rubber band cut in half that could wiggle, and you could stretch it out, and then you could bring it back to its regular size. And truly, he thought that the scientific community would just be so astonished by this discovery, when in fact they really didn't have a reaction to it. But that's besides the point. Still, even though finding out that strings were the key to unification, you still had some pretty big anomalies that would turn out to be fatal if they weren't fixed. And they were very confusing in this. So a way to describe some of the anomalies would be this. Each of the equations represents one physical property of the universe. In this equation, you would figure out that x equals 1. Well, and on the other equation, x would equal 2. So, but you can't have two different values for x. It doesn't make sense. It's just a small example of what an anomaly would be like, but the ones in string theory were much greater. Now, as Schwartz continued his search for what string theory was, he met a man who was willing to help him by the name of Michael Green. And Michael and Schwartz continued very hard to figure out what. The two decided that they needed to find a way to get rid of these anomalies, and they did this so by describing gravity and the other forces. At the end of their experimentation, they finally figured out that the equation to string theory was finally rid of anomalies, that they had successfully made an equation that string theory could finally be based off of. In their experimentation, they also figured out a way how strings vibrate. And the way they vibrate determines the outcome of what the matter would look like. Almost like if you were to have the strings on a guitar. One string makes a different sound than another string, which you hear this, and you don't get the same sound. You get maybe a lower and a higher pitch. It's kind of the same concept between strings. By adding strings into the equation, as I had stated before, you get quantum mechanics kind of calming down and being more smooth, and it just vibrates, besides the whole chaotic world that it used to be in. But strings, they require an extra dimension of space to work, but that doesn't work out with our back and forth, up and down, left and right, and one dimension of time that we've become so used to knowing. Einstein proposed that space-time was full of warps and ripples, but there wasn't really a place that there would be another dimension. But a person named Kaltuza, if I think how you pronounce his name, proposed that there would be another unseen dimension that could be hidden inside of these warps. which created something different, because we view our world as long and stretched out. And at times when we look at it, you can rotate around it clockwise and counterclockwise, as if you were traveling on the surface of a ball. But in his unseen dimension, you have our world that is like that, but then you have smaller, even tinier ones built inside upon that, and it just keeps building and building until you get 6 dimensions that would be proposed on this idea. Upon all these new discoveries, more and more people kept getting interested in string theory, which made some of the modern string theorists very happy. But it also kind of became bad. As more and more people studied string theory, they figured out more and more solutions to string theory. And in the end, we were proposed 5 different propositions. 5 different ways of viewing string theory. Well, could that mean that you could have maybe the smartest minds in the world working on this? And then if you keep discovering, you can dig up more and more till you get 50, 100? It kind of would declare that string theory maybe is just something that wouldn't work. Would it? Though with these 5 different ways of viewing string theory, they had some similarities. They all used strings, but some were closed, some were just straight, and it never really worked together. It was like an out-of-tune symphony. It just didn't sound right. So scientists had to prove which one was right. And if one could be proven right, couldn't all they be proved right? Could one of the 5 different theories for string theory be our universe, and then there'd be 4 other different ones? 4 left, 4 other universes? Different parallel worlds? Could that be possible? Some people thought it was just crazy, like it was science fiction. And there were others that wanted to prove that it was true. But how could we, when we can't even see strings? So, in these 5 different dimensions, you kind of get the concept of that time, in a way, time is money. And that the faster you go, it reduces the time you take. This reduces the time you take to get to one place or the other, to point A to point B. But you can never travel faster than the speed of light. So if you're traveling a long distance, how could something so flat take you faster? Well, you can also use that in a wormhole. And it's like a bridge between these 2 different points. It warps. It takes space-time and it warps it. So if you have a distance that's this long apart, you fold it up and now they're this close. You can kind of view this when you look at a piece of paper. I'm going from point A to point B, but it's a long distance and I really don't want to travel that far. So I can just fold it up, and there's point A, and point B, and it's a much shorter distance. But in the fabric of time-space, you can warp it and you can twist it and everything, but you can't tear it. And you can't just recreate a wormhole out of nothing. It has to be put there. You can't create one by ripping and tearing time-space. So if I wanted to travel from here all the way to school, I couldn't do that because I can't tear time-space. So I guess wormholes you have to really look for wormholes. But in quantum mechanics, space could theoretically rip. And if it did rip, what would happen? Would it be something really horrific? Well, if a rip would occur, the strings in quantum mechanics do calm it down, and the strings form tubes, which then encase the rip, and it acts kind of like almost like a protection, like a force field around the rip. So that way, really nothing bad does happen. According to string theory, our universe just can't be one dimension. There's multiple dimensions, possibly 10, but you have 5 different ways to view the theory. They're all similar in ways. They all use strings, but sometimes the math's just all different. In 1995, a man by the name of Ed kind of found a new perspective upon string theory. He viewed that all these 5 theories were just different ways of solving the one master one, and everyone was just looking at a different way of viewing string theory, and that there really was just only one solution to it. And his theory was came up with the M theory. And truly, no one really knows what the M stands for. Like mysterious or matrix or murky, because we don't really understand a lot of the stuff we study sometimes. This unified our way of looking at string theory. We finally had one actual true string theory to finally look at. But in this new M theory, it required another dimension, which making in total 11 dimensions. Now, in our universe, we have 4 different dimensions. We have a dimension of time, up and down, back and forth, and left and right. But in some dimensions, you have more, and that's processed by the degree of freedom. And the degree of freedom, the more degrees of freedom that you have, the more you're able to do in a certain universe. You also have things called membranes, or shortened brains. And what that does is they can be 3-dimensional, or they can kind of grow to the size of a universe. But according to these brains, you can maybe possibly get a parallel universe, or a universe that could be just inches from my face that I can't see or touch, and it could be so similar to our world. And that's because it's on a different brain, and it can't just leap off into ours, because the atoms and particles attached to one brain specifically will stay on that brain. But there's kind of a catch. You can have sound waves, they can leave your brain, because it'd be like if you're on a pool table. You have the cube, you have the balls, and they clack together. The sound's going to radiate off that table, but the balls aren't going to stay. And also you have gravity, and but really we think gravity's strong, but it's actually kind of weak, because I can drop my pen and just pick it back up, and I'm defying the laws of gravity because my muscles pick it up. And magnetism is stronger than my muscles. So it can be, so you have a gravitron, which seeps off one brain and can go on to another. So in theory, you could technically, in years to come, you could technically probably communicate with other beings, if there are any, on other brains, just by using gravity. Kind of weird. That's also why you can also have, that's why matter and light don't come off the brain. It's kind of suggested that they're like strings cut at one point, like a stretched out, cut in half rubber band. You have it, and it's attached to the three-dimensional brain, and it can't move. But a gravitron is just a circular string, and it's not attached to anything, so it's free to float off and wherever it wants to go. We really don't know if there could be a parallel universe next to us, and we really don't know if it in any way can impact our lives right now. For instance, there is one theory that we could use that probably describes the beginning of our universe entirely: the Big Bang. Bang is when our universe was into the size of something so small and so tiny. But at one point, something happened inside of this tiny little ball of energy, and our whole entire universe just scattered among the solar system. And it just, no one really knows what happened to the Bang. There's a lot of problems and different theories and problems within these theories that we're just really not so sure of what happened. At the very beginning of the Big Bang, we kind of see that nothing makes sense and that our laws of physics don't apply. And so you have to wonder, what was the Bang? What really caused the Bang? Well, one theory you can involve is string theory. And that's that there really wasn't a beginning of the universe. And that kind of upsets some people in the scientific community, not having a very beginning of something. It's kind of suggested that that you have two different brains, and they're coming closer to each other. And at one point, they're going to strike. And there's so much energy just bundled up in there that energy has to go somewhere, which it creates a bang, creating another universe. Some scientists believe that since there was no beginning, that two brains striking each other is very common and that it does happen. And if this were true, then theoretically there's got to be a brain on its way coming towards ours. And eventually it's going to strike our universe. And they'll collide, and there'll be another burst of energy creating another whole entire universe, starting it all over again. At times we kind of look to the string theory to try and help us solve the Big Bang, because if strings were so tiny in the very small space that you started out with, they're going to leave some mark on the world. But when the whole Big Bang happened, when the bang happened, and all of this matter and energy got scattered across the solar system, you're gonna see traces of the strings when they expanded somewhere. We just haven't found them yet. Maybe they could be written in the stars somewhere. We have no idea, and it'll probably take us more years to figure it out. But people also think that string theory, its views sometimes are just like scientific, and they don't seem plausible. Well, it's because we really can't test string theory. So in truth, we really don't know that much about string theory. It could help us be able to unify all the different forces, general relativity and quantum mechanics, together, but we still don't know. We haven't been able to fully see a gravitron leave a brain, though there are experiments that are being conducted to try and view that, but we really just don't know. So we have to keep trying and keep guessing. And maybe this whole guess that we're doing isn't going to work out. Maybe it's just a complete faux pas that we're doing right now. And it's going to be viewed as either a scientific breakthrough or just a big scientific mistake. All we can truly tell is that maybe we want something. And in maybe 30, 40, 50 years' time, we'll know if all of this experimentation really does pay off in the end. Thanks for watching.